What we're going to do is we're going to look at the potential energy diagram and, more importantly, the section we skipped before. To do this, what we'll do is we'll look at the reaction of hydrogen gas with chlorine gas to form 2HCl. And from our previous unit, we are able to get our enthalpy change for this, which is negative 185 kilojoules. Now, when we go to plot our graph, we know that our potential energy goes on our y-axis and reaction progress goes on the x. We're going to say that our reactants have some amount of potential energy. This is the energy, this potential energy would be to the position of all of the molecules and the energy also associated in their bonds. And because we know that it's a negative 185 kilojoules, we know this reaction is exothermic. And so my products will have some energy associated with them as well, but it's less than my reactants because this is an exothermic reaction and this energy is given off. Now in a previous unit, this area between these two regions we just drew with a straight line and we ignored what was going on in it. What we're going to do is we're going to look at this region more closely now. Okay, but we do know that my enthalpy change is 185 kilojoules and it's negative because it was released. Now, if I wanted to go in a reverse reaction, we also talked about if we flipped reactions, then we would change the sign. So if I wanted to take two HCl gas molecules and form hydrogen gas and chlorine gas, it cost me 135 kilojoules. Now let's take a deeper look at this region in between here. Now we know that as two molecules approach each other to collide, their electron clouds are going to repel each other. This causes their potential energy that they have, their kinetic energy to be converted into potential and will slow down their progress towards each other. If they're moving with enough kinetic energy, they can maybe approach each other and collide, and then they can react. Now our activation energy is the minimum energy required for them to overcome their repulsion of their electron clouds and let them collide with sufficient energy to react. So if we look at our graph that we had before, and all we've done is taken the line that we use to join our reactants and products out, we can first plot this initial line. And what this initial line shows is it shows that as my two molecules approach each other and get ready to react, and at the peak here is where they react and they collide, that their potential energy is increasing. And this is due to the fact that as they approach each other, they're going to slow down and convert their kinetic energy into potential energy. And after the point of collision, they're going to bounce off of each other and the products will go off in their separate directions, causing their potential energy to be converted into kinetic. In this graph, we have a region where we're mainly breaking bonds, and this is as they approach each other and reach the peak, where that's where the collision occurs. And they have a region of mainly bond formation, where after we break our bonds, we form our new bonds. And this is sort of just after the collision as well. The peak of the curve, where they collide, is a region that we call our activated complex. Now, the activated complex refers to a collection of intermediate structures, and this is where all of our bonds are basically half broken and new bonds are half formed. They can be represented in more than one way, but for our simple molecule that we have here, we can see that the bonds between the two hydrogen molecules are almost broken, and that's why it's represented with a dashed line. And the bonds between the hydrogen and chlorine are almost formed. That's why it's represented with a dashed line. And also the bonds between the two chlorine atoms is almost broken. That's why it's represented with a dashed line. So we have our activated complex at the top. Okay, and so this energy that is required to go from my initial state, where my reactants are, to the peak of this curve is called my activation energy. And this would be my activation energy for my forward reaction, because it's the energy required to go from where the hydrogen and chlorine gases are to the very peak. If I wanted to see my activation energy for the reverse reaction, it would be the energy to go from where the two HCl molecules are to the peak of the curve as well. And unlike the enthalpy change, the activation energies for the forward and reverse reactions are not numerically the same. They do not have the same magnitude, because I have to overcome or add all the energy back and get up to my peak, and then I get some of it back. Okay. Now, one of the things we can notice, and we've talked about in class, is that the addition of a catalyst provides an alternative reaction pathway that has a lower activation energy. So we can see that here, where if I add a catalyst, I don't have to add as much activation energy, so my peak doesn't go as high, and also my reaction is completed sooner. And so we can see that my activation energy for my forward reaction with the catalyst is much less. Now, we don't talk about what a catalyst does, but what a catalyst can do is when it provides a reaction, an alternative reaction pathway, it really provides what we call a different reaction mechanism. And so what we can see down here in the purple is I'm proposing that my reaction occurs in a series of steps. And so I have 3 steps that it's occurring in. And so what we can see is that there are 3 steps, so with the middle step being the slowest. So what I can do is I can take this region where I showed my catalyst and really break it up into 3 peaks. 1 peak representing each step in my reaction mechanism. And I said that my middle one is my slowest step, so therefore it will have the highest peak. Okay. Now, the things that are circled we are calling reaction intermediates because they're not found in my overall reaction. And I would expect to find my reaction intermediates in the troughs in between each of the peaks. Right here.